Hello, welcome everybody to the academic training series. Today is a special day because it's the first time that we are doing an introduction of a programming language in the academic training series. So let's see how it goes. But you know that here at CERN we have so many experts in Python, C++, Java, Scala, and so on. However, okay, we are starting having a little experience in Go, but we need an expert to help us, okay? So that is why I'm super happy that Francesc is here with us. Wow, he's really a passionate programmer in Go. He was working in Google in the cloud platform. He joined the Go team. He is also having a channel in YouTube, just for fun, where he's co-reviewing all the time. And he's a not-stopping guy because also he has a startup called SourceD that is even applying machine learning and Source. So I'm really, really pleased that you are here. So join me to welcome Francesc Campoy.
Thank you. Thanks for inviting me. Hi, hi everybody. I'm Francesc Campoy, and I'm going to be giving a 3-hour talk over 3 days, so we don't die. So it's going to be 3 days, and today we're going to be talking about the introduction, the basics, and the type system of Go. So as Maria said, I work at Source. I'm VP of Product and Developer Relations, but before that I worked as a developer advocate at Google, where I did a lot of cloud things, Kubernetes and TensorFlow and all that stuff. But on top of that, I was part of the Go team. So I was a contributor to the programming language, to the core, to the standard library, and I spent a lot of time reviewing code, which was fun. I'm also on Twitter and on GitHub, if you want to find more Go code there. And also, this is a picture that I generated myself with machine learning based on Go, so yay. And as she said, I also maintain Just for Fun, which is a YouTube channel where I talk about Go all the time. So there's going to be a lot of topics that I'm going to be mentioning really quick, and probably there's a much better video and longer explanation in this channel. And I'm almost the most successful Go programming language channel. I'm only like 1,000 away from the official one. No, 2,000 away? Yeah, 2,000, that's pretty sad. But yeah, I'll get there one day. So on the 3 days, we're going to be covering as much as possible. We will not be able to cover all of the things Go. So I'm going to be skipping a lot of things that I consider to be either too complex or too boring. So we will not be talking about if statements, because you know what they are. And also we will not be talking about the most advanced pieces of Go, because probably you don't need them yet and they're going to confuse you. But if you want to ask about them, feel free to do so. So today we're going to be talking about the Go basics. What is Go? And what is the philosophy behind it, and then the type system. How many of you normally write in C++? Okay, Python? Okay, so for C++, you're gonna hate it. It's normal, you'll get used to it. I was a C++ developer, and when I saw that there was no templates and you don't get to manage memory, I was like, what? But then there's no templates and you don't get to manage memory, which is good. And for the Python people, you're actually going to feel at home. It's very, very similar, except that most of the things that fail at runtime in Python fail at compile time in Go. But the type system is actually very, very similar. On day 2, we'll talk about concurrency. There's a lot to be said. And then on day 3, we'll talk a little bit about performance analysis and tooling, and basically, once you bring in a program, how to make it better. So that is the goal, but it depends on what you ask. So I'm going to try to leave Q&A at the end as much as possible. Feel free to ask any questions about the things that I explained or all the things. And also at the end or at the beginning here, no, my email is not there. But if you say you can send questions that I can answer later on at campoy@golang.org. So, day 1, welcome. So today we're going to be talking about the Go basics, the type system, and then we're going to see some of the things from the standard library, but I decided that is actually not that interesting. So we're going to be just seeing some types that might be useful, that you're going to get to use all of the time when you're using Go. But that's a little bit less important because it's something that you can learn as you go. and then Q&A. So what is Go? Go is an open source project. Yay, open source. And it includes the language specification, the runtime, which is actually many runtimes nowadays. Then two compilers, GC and GCGo, except that now it's more than that because there's also LVM and a bunch of different backends, and it also compiles to Node.js, to WebAssembly, compiles to many things. So those two are the official ones, but the community keeps on adding more. The standard library, and a bunch of different tools that we'll talk about at the end, and then documentation. Now, the interesting thing is the language specification and the standard library and its documentation are covered by the 1.0 backwards compatibility, which means that if you write some Go code now, it will compile forever as long as we're using Go 1. Whatever. We just released Go 1.12 release candidate 1, like I think this morning, and this still works. So if you have something that you wrote back in, I think it was 2012, it would still compile. And this is cool. I don't know many languages that actually do this correctly. So if you're using dependencies, then, depends on the dependencies. But in general, everything will still work, which is very nice. So yeah, 2012. The important thing is this means that it will build and run. You need to recompile the programs, which is good because actually the compiler keeps on getting faster. So if you wrote something in 2012 and you get the code and you compile it again, you get kind of the same binary, just like faster, which is nice. And this is the best thing we've ever done. And hopefully we'll not mess it up by having a Go 2.0. Because for the Python people, you might have heard about Python 3. We don't want to do that. So we're trying to avoid it. So what is Go about? Go is about composition. It's about composition all the time. About composition of types, and we're going to see how the type system helps with this. About the composition of processes, and this is all about concurrency and how if you have a web server, an HTTP server, an SSH server, you can run them in the same process very easily with just one single command, one single instruction. And then large-scale systems. So the way we package all the idea of how Go packaging system, libraries, and all of these things work together, the whole idea is to maintain large code bases in a nice way. This is something that has been successfully proved possible internally at Google, and it also has been successfully hard to do externally with Kubernetes. If you see the Kubernetes code base, it's actually kind of hard to follow. So Go helps, but you need to still be quite strict on the best practices you follow organizing your code. So, hello, CERN. This is Go. So, how many of you this is the first time you see Go code? Okay, wow. So that's going to be fun. So yeah, so let's go. So let's go through this a little bit. In Go, everything is part of a package, always. There's nothing that is outside of a package. So we have package main, function main, that is the entry point to any Go program. Okay? And the function main is a function that is a little bit special, but just because it's the entry point. Other than that, it's a pretty normal function that doesn't receive any parameters and doesn't return anything. It's the func main. And then we're calling func.println, which prints something. So yeah, all Go code lives in packages, and packages are composed by 4 different things. Types, functions, variables, and constants. Those are the 4 things you can have in a package. And that's it. There's nothing else in Go. So packages can be tiny. The errors package in the standard library defines one single method, a function called new, so you can call errors.new. Some others are way, way bigger, like the HTTP package. It's pretty humongous, because HTTP is hard. Normally when you're defining your own packages, the idea is to keep them as small as possible, keeping coherent, but not going too small that at the end, every single program using your library needs to import like 20 packages just to do something basic. Oh, and also, the way to see whether something is exported is not by using public or private, it's by the first letter of the identifier. If it's uppercase, it's exported. If it's lowercase, it's not. And that's it. And this is the same for types, constants, methods, and variables. Same thing for everyone. So, back to the program. Here we're importing thumped. It's pronounced thumped for reasons. And the idea is thumped contains, it's the short way of writing format, and it's all about formatting and printing. So when you want to call the println function that prints with a new line at the end, you're going to call thumb.println. Now, what will happen if you do this? You're going to get two errors. You're going to get one error saying, hey, you cannot call println with a lowercase because you're outside of that package, so you're not allowed to do so. And a second one is, and by the way, that doesn't even exist. Okay, so there are two different things. Even if it existed, that would not be allowed because basically it's a private thing. It's non-exported. We don't use public-private. We use exported, not exported. But this idea works. So what else about packages? So the packages we've seen so far, thumbed, are part of the standard library. So thumbed is formatting and printing. You have other ones like encoding/JSON. And you're going to import it by saying import encoding/JSON, which is JSON encoding and decoding. And if you want to find all of the packages in the standard library, golang.org/pkg is a website with all of them. The convention here is that when you do import thumbed, the identifier that you're going to need to call println is thumbed. So you do thumb.println. And if it's longer than one component, you choose the last one. So encoding/JSON would be JSON dot whatever, or math/ran is ran.intent. Now, this is a convention, which means that everybody follows it except for some people. And that happens. So if you're using things like gRPC, for some random reason, they will not follow that convention. So there's a way to import things where you can do import a name and then the package you're importing. And that's an import alias, so you can fix this issue. But in general, you should not have that issue in general. I'm pretty sure that was supposed to have, oh yeah. So yeah, more packages. So there's standard library packages and packages that are outside. The packages that are outside, they follow the same idea. They have an import path. And the import path for the standard library looks like just some path in your directories. But when you go into the import path for packages that are outside, it's going to look more like almost a URL. It is not a URL because it doesn't have any schema or anything like that, but it looks like it. And actually, when you're pulling data, it's going to go look inside of github.com/golang/example. So that's how the tool, the Go tool, is able to figure out when you say, I'm importing that, it's going to be able to find that dependency even if you don't have it in your laptop, which is dangerous. And we'll talk about vendoring and managing dependencies and all that stuff. But by default, when you're getting started, that works, and it works really well. So golang.org/pkg was for the standard library. Godoc.org is for everything, including the standard library, but anything that is open source on GitHub or GitLab or Bitbucket, and whatever else exists. So if you do this, go get that package there, github.com/golang/example/hello. When you do this, there's gonna be three different things that happen. First of all, we're gonna see whether we have it on the computer, and if not, we're gonna download the code. Second, we're going to compile that code. And since this package, I can tell you, starts with package main, that generates a binary. So when you look at ls go path, source, and the import path, that is where the source code that you just downloaded ended up. Okay? So that's how you store all of the source code in Go. If you know about Go modules, ignore them. I will not be talking about them because they're not official yet, and it's just going to make it more complicated. But if you want, we can talk about them a little bit later. But without Go modules, this is how Go is structured. You have Go path, and inside of source, you have all of this code organized by their import path. So in here we have hello.go, and hello.go is simply like a hello CERN that we had before. So when you go into go path/bin/hello, you have the result of compiling that code. Okay, so that's how basically you're going to have the things, go path/source for your source code, go path/bin for the binaries. Go path is an environment variable, and you can set it up if you want to. For instance, for me, I set it up as home, which means that my home/source contains all my source code. Go or not, I actually put all of the source code in there. Much easier for me to figure out, but you can do it as you want. If you do not set it up, it will default to home/go. So if you do go get whatever, it will be and the home/go/source/ the import path. And this will disappear soon. Go path is a thing that we've been using since Go 1.0, but everybody has somehow hated it over time. And we got to the point that we're almost getting rid of it. But it's still not official, so that's why I'm not going to be talking too much about this. But this slide will be deprecated probably 6 months or a year, depending on Go 1.13 or 14. So yeah, inside of there, you're going to have your workspace, and your workspace has three things: source, bin, and package. Source contains the source code, bin contains the binaries resulting of the compilation, and PKG contains a cache. So you can get rid of it, and you don't need to care about it at all. You can delete it at any point, and everything will keep working. This is just to make compilation faster. And again, this will disappear soon. So do not think about that PKG too much. It's just something that appears, and you can ignore. Okay, so another program where we're going to be saying hello CERN, but reversed. So in order to do that, we're going to be using the string util package. And the string util package is defined under github.com/golang/example/string util. So when you write this code, and you put it in your machine and you do go build or go run, what is going to happen is Go is going to parse this, figure out that github.com/example Golang example string util, whether it's in your machine or not. If it's not, it's going to download the code, put all that dependencies plus your code, compile it, create a new binary, and put it on the go path/bin. And if you run it, it would say hello CERN backwards, which I don't know how to pronounce. So more things on Workspace. There's vendor directories to manage dependencies, and I will not be talking about those. There's the dep to manage dependencies, or Go modules, which is the new solution. There's also a thing called internal directories for if you have a really large library, only exported or not exported per package might not be enough. So you can actually do that per group of directories, which can be helpful. And then the Go list tool. If you want to learn more about how source code is stored in your workspace, you can see that workshop. There's a full-day workshop on Go tooling in general, and it starts with how to manage your workspace. So let's talk about something more interesting, in my opinion, which is the type system. So the Go type system, the whole idea of the Go type system is that it's as simple as possible, and it's also as, not cohesive, but what's the word? I forgot the word. It's as, everything tries to be always the same, so as little rules as possible too, but also as practical as possible, so those rules will be broken sometimes by the language in order to make things faster and easier to write. So let's talk a little bit about how this works. So Go is statically typed, like C++, not like Python. So if you write var s strings equal hello, and then you try to put a float in there, you're going to get an error message saying you cannot use true type float64 as type string in assignment. That is something that the compiler will complain about. Okay, cool. But when you write it, actually you're never going to write var s strings equals hello, because that is pretty repetitive. So hello is a string. You don't need to say that it's a string. So actually you could do var s equals hello. Or even shorter, you can do s colon equals hello. The colon equals is what we call a short variable declaration. Some people call it the Gopher Operator, because if you look at backwards, it kind of looks like a gopher with the teeth. And I didn't make that up. So, and the whole idea is that you have all of the type safety of C++, actually more type safety than C++, but with basically as much typing as, or as much writing as in Python. That's the idea of making the writing as easy or short as possible while keeping all the guarantees that you get of type safety. So let's go back to variable declaration a little bit. You can declare variables by giving the name and the type. So var number int declares an integer name number. You can also do var 1, 2 int. So that declares two integers, 1 and 2 of type int. You can also give a value. So you can add 1 or 1, 2. So you need to have as many values as you're declaring variables, obviously. And actually, once you do that, that starts to be kind of repetitive. So you can use the short variable declaration and drop the var and the type and use colon equals. So you can do number equals 1 or 1, 2 equals 1, 2. And that's what you're going to see most of the time in source code. You're going to actually see that short variable declaration basically everywhere. So this means that there's default values for types. And how do they work? Well, see, if you have int, an integer is going to be an int. If you have a float, it's going to be a type named float64. If you have a string, it's a string. If you have a boolean, it's a boolean. And that's pretty much it. Those are the only literal things that you have in Go. So that's pretty straightforward. So now that we know the basics of how you declare variables, let's talk about the types. There's two kinds of types in Go. There's concrete types and abstract types. And that's it. That's the whole, all of the kinds of types that you need to think about. Concrete types are the ones that we're going to be talking about first. And concrete types are about memory. How do you set something in memory, right? So you have things like int 8, 16, 32, 64. All of these are integers. It's not about the behavior, right? It's about the size and what you can do with them. So that's basically what you're storing. And then you can attach behavior through methods. And we're going to see that later. But let's talk about a little bit more about the different types. So you have numerical types. And Go is pretty picky about types, especially numerical types, because we want to avoid having errors on the... we want to avoid as much as possible overflow errors and things like this. So if you combine two different numerical types that are not exactly the same, it will not compile. There's no implicit conversion in between numerical types. So if you want to add an int32 and an int64, you need to say, I'm passing int32 to int64, which is safe, or int64 to int32, which is YOLO, right? That you need to decide what you're doing, and then the compiler will be okay. But you need to say it first. You need to be explicit. So there's all of the ints, the unsigned ints, complex numbers, which I've never used, but maybe at CERN you will get to use them. And there's also two things, which is byte and run, which are characters. Byte is not really a character, but very often we use them as characters. And they're an alias to uint8. It's an unsigned integer of 8 bits. And run is a UTF-8 endpoint, code point. So here you're going to have int32, which is kind of weird because it's 4 bytes, but 4 bytes is more than what a run actually fits. Run normally it's smaller than that. It's only 3 bytes. But UTF-8 is complicated, and we were not going to define an int24. So that's why we use int32 for this. So for instance, if you are going to iterate over all of the letters in a string, in Go, you do not get bytes, you get runs. And this is important because if you are managing things with UTF-8, like you have, for instance, you're writing something that contains Chinese, that Chinese character is going to be considered as one character, not a series of bytes. And this solves a lot of problems in Python, at least problems that I had. Python 3, I think it comes with a new kind of string that solves this too. There's also, so int, uint, and uint_ptr. These are kind of special because the size is not known. The size depends on the platform. So int is, depending on your machine, is 32 bits or 64 bits. That's going to be the size. Uint, same. And uint_ptr is the size of the pointer on your machine, which sounds like it should be the same as the size of whatever you're managing, whether it's 32 or 64, but there's ARM compilers that do weird things. So that's why we also have those. So if you want to convert a pointer to an integer, you're going to be using uint_ptr. And then others, we have bools, strings, and errors. And we'll talk about errors a little bit later. Okay, so we have those predefined types. How can we define new ones? So we have a bunch of different ways to do it. The first one is arrays. Arrays are arrays of something. So you can say an array of 3 ints. That's how I declare it. The square bracket, the size, square bracket, int. And an array is of, so the type is 3 ints, right? So if you have 3 ints and you have 4 ints, those are different types and you cannot play together. They cannot play together. Okay, so arrays are pretty useless, and you should not be using them most of the time, to be honest. I get to use them only when I'm showing like little games with a deck is exactly this number of cards. Sure, maybe you can use it, but otherwise you're going to be using slices. And slices are like arrays, but the size is dynamic. So they can grow, they can shrink. And the type looks very similar, but there's no size, right? So you remove that size, and now you have a slice, not an array. You also have maps, which are like Python dictionaries. So you have a map from string to int. You have functions. And functions in Go are cool because they're exactly like any other value. You can pass them around. You can put them inside of maps. You can pass them as into. You can put them inside a parameter or return it as a return value from a function. You can do anything you want. So this feels a lot like if you're doing JavaScript. In JavaScript, you can do this all the time very easily. In C++, if you're trying to do things like this, it's much more complicated unless you're using like a functional. I think there's a functional package in the standard in the STD or something. I do not remember. It's been a long time, but there's some ways of doing it. And in Python, I actually do not know. There's lambdas, but I don't know how much you can play with them. Go uses functions as first-class citizens. So you can whatever you can put an int, you can put a function. And then we also have channels. And channels are something that we'll be talking about tomorrow because they're part of concurrency. But a channel is a channel of something, and they have directions. So basically, you can pass values into them. You can say I have a channel of integers, and that's bidirectional. You can also say I have a channel where I can only read from, or a channel I can only write into. And those are the three different kinds of channels that you can have. Also for functions, functions can return many types. So here, for instance, this function we could imagine is ASCII to integer, so it's parsing something, it's returning the integer, but also an error if that could not be parsed. So that's how you write it with that extra parenthesis at the end. And then two more kinds of types, structs and pointers. Structs are like classes, but Go doesn't have the class keyword. We don't have class. So instead we have struct, like in C. And it's actually very similar to that. So we have a type person here, which is a struct, and it has a list of fields, 2 fields. Name is a string, each year is an integer. You may have noticed that if you're writing C++, all of the type names are backwards. And this is fun when you're switching between languages. You end up getting used to it, and then it's fun when you switch to another language. So this is actually, the reason for this is because something like that actually makes lots of sense. A type func int to int is a func that gets an int and returns an int. And you can actually keep on adding things in that order. So that idea of writing first the name and then first the name, then the type, or the return type at the end, all of this comes from Pascal. And that's where it's coming from. The creators of Go have created many languages over time, and they've been in the tech community for quite a while. So they've used pretty old ideas from very old languages too. And we also have pointers. And pointers are like any kind of pointers you might have used, except that you cannot do much with them. If you have a pointer and you try to add 4 to it, it doesn't work. You cannot do that, because what are you even doing with that, right? Except that you can. You can with a type called pointer that comes from a package called unsafe for a reason. You should not be using that unless you're doing things like reading some specific area in memory or things like this, things that are a little bit more low level. You can also do that, but by default it's not allowed. Okay, so let's talk a little bit more about slices and arrays. I talked about arrays and I told you don't use them, and that still is true. As much as possible, use slices. They're much easier to use. How do you declare them? So you can declare them by using, let's talk about the one on the left. So var s int, you declare in the new variable, the name, and its type. When you do that, you get a nil slice. It's a slice that has not been declared. But that's fine. You can actually do anything with that. You can get the length. So you can print the length is 0, because there's nothing in there. But also you can append elements to that. So append is the predefined function that you use to add elements to a slice. And that's how you grow slices. And then another option, if you want to, say, predefine a big buffer, whatever you want to do, you can use make. And make receives first the type, and then the length that you want to use. You can also use capacity and length So a little bit more advanced is basically when you want to have a very large slice, like a slice that could grow really fast without having to do reallocations. But at the same time, you want to start with something that is completely empty. There's a way of doing that, which is, here would be make int 0, 2 in this case. If you do this with make int 2, you're creating a new slice with 2 elements. And those elements will have the 0 value. And the 0 value in Go is well defined for all types. Unlike C++, in C++, sometimes a pointer might not be, if you don't set it to 0 in the constructor, you might end up having weird issues and memory corruption and things like this. In Go, there's always, everything is set to the 0 value of the type. So pointers is nil, integers is 0. So this will print 0, 0. You can also do sub-slicing, so similar to Python. So you can get a section of a slice. Important thing is you cannot use negative indexes, unlike in Python. In Python, you can -1, and here you will have to do length of the slice -1. The reason for this is that there's actually a whole class of bugs of indexes going wrong and going negative, and rather than failing, it just keeps on getting different values. So in order to avoid those errors, we disallowed having negative indexes. And also, something different to Python is the fact that when you're sub-slicing something, you're not copying that array. There's actually a slice is a window into a backing array. So if you have this slice 0, 1, 2, 3, 4, 5, you have a slice of the same size as the backing array that contains 0, 1, 2, 3, 4, 5. But if you get a sub-slice, that sub-slice is going to be pointing to an area of the same backing array. So if in T I change one element, I'm also changing it in S. So you need to be careful with these things. This means that it is much faster because you're not copying memory as often as with Python. But it also means that you're not copying the memory, so you can actually have side effects like this. So if you want to avoid it, you're going to need to copy that slice into a new slice. Maps can be made with make. With slices, I told you that if you have var as slice, that works. With maps, that's not true. Maps are actually more complicated, and if you declare them like that, with var as map or whatever, that will compile, but as soon as you try to use them, it will panic. Panic is like exceptions in Go, but they're actually exceptional. They only happen when things really go wrong. We do not use exceptions in general. So if you use make, you're going to create a new map, and then you can assign things to the map. You can delete keys with the delete keyword, and you can then also have what we call type literal. So type literal is the type and then the brackets and key and value inside. Similarly, here that is also type literal for slices. The type, square brackets, and only the elements because this is a slice, not a map. You can print the size, and also you can access the elements. So that's basically all of the things that you do with maps. Now, let's talk about functions, because functions are the cool things in Go, I'd say, at least regarding the type system. So you can declare a function that gives it an int, returns an int. Easy. You can declare a function that given 2 ints, returns an integer and an error. 2 integers, you could do x int, comma, y int, or x, comma, y int. That's the 2 things are exactly the same. You can do split host IP, for instance, and given a string, returns 2 strings. And you can name them if you want to. The whole idea of naming those returned values is it makes it clear, right? In general, you will not name the return values, but in here, otherwise, which one is the host and when is the IP, if you just say string, string. Makes it easier to understand. You can also declare a variable of type function. So this is a variable, even, of function int to bool. And when you declare this, the function is nil. So if you call it, it will panic. But other than that, it's basically like a pointer, and you can pass it around. And you can also declare function literals. And a function literal is what in many other languages we call lambdas. In Go, we just call it function literals, because you have slice literal, map literals, struct literals, and function literals. They're all the same. And here, for instance, we're defining even as the function. Now, even is a variable, so it can change. You can change the values, you can pass it around, you can get the pointer to it, you can do anything you want, as with any other value. Then we have more functions, and these are closures. And the cool thing here is that I'm defining a Fibonacci function that returns a function that returns integers. So when I say that, and if you read the type signature, it makes sense. I'm defining a function Fibonacci that returns a function that returns integers, right? If you think about how you write in Python, easy, done. Think how about you define this in C++. It would be slightly more complicated. You would actually need to go with some patterns, probably, unless you know how to use the pointers really well. So in here, what we're doing is returning a function. And this function, what we're doing is every single time it's called, it's going to change the values of A and B to be B and A plus B. So that is basically what Fibonacci does. There's a couple of interesting things here. One is the fact that we're doing that parallel assignment. When you do A comma B equals B comma A plus B, that assignment is done both exactly at the same time from an abstract point of view. Obviously, that doesn't happen, but you can do that. Also, if you want to switch two variables, A to B, you could do AB equals BA. You can also do that. So that's like Python, but not like C++. The cable is falling. So for instance here, what we're doing is we're referring to A and B. So every single time you call the function fib, a new A and B will be declared, which means that every single instance of that function we're returning has their own private A and B. So if you call fib twice, you will have two different Fibonacci series. So you could start here and do 1, 1, 2, 3, 5, and then here would start 1, 1, 2, 3, 5, because they're using different instances of A and B. So now if I did this, and basically I'm moving that variable declaration AB outside of the function, now since we have lexical scope, what's going to happen is that all of the calls to fib are going to share the same A and B variables. So now, if you define two functions fib, this is when you start 1, 1, 2, 3, 5. Here, when you call it, it's going to return 8 directly, because both are sharing the same state. Okay? And this is something that we do all the time, actually. Closures in Go are pretty normal, and they're pretty powerful because they're really easy to follow. If you think about languages like in JavaScript, doing this is much more complicated because of the way this works and all that stuff. In Go, we don't have this. There's no such concept of this. So this means that it's like any other variable, it's just lexical scope. Okay, so structs are boring. You can define a struct literal by using type, braces, and the values inside. And the values you can either give as many values as fields you have, and then you don't need to give any name, or you can also choose one of them, and then you need to give the field name and the value. I do recommend whenever you're using the standard library to use this method, because the backwards compatibility guarantee does not include adding new fields. So new fields to a struct could be added, which would break that code, but not this one. And then also you can access the things by me.name, that would be my name. Okay, so now we have all of the ways of creating new types. So the next step is we're going to be talking about how to define methods. So to define methods, you define, it's basically like a function, but it has an extra parameter. And that parameter is an explicit parameter that goes in between the function name and the func keyword. And that is what we call a method receiver. Okay? So for instance, we can define a major method on the person by saying p.person. We do not use this. We do not use self. We use a name that matches the type. And then, for instance, we're going to return p.ageyears is equal or more than 18, and that's going to be our method. Now, if you do this is like a parameter, right? So it means that you're passing a copy of person, which is fine in this case. But if you wanted to modify the receiver, you need to pass a pointer. So in here, for instance, if I want to say it's your birthday, so year plus 1, you're going to need to pass a pointer to person. Otherwise, you would be increasing the field age years of a copy of the person, which would not have any side effect. So it's basically like any other parameter. It will work exactly the same way. Because Go is pass by value. And when we say pass by value, this is actually really straightforward. It just means everything that you pass is always a copy of the original. Now, the thing is that that copy might be pointing to the same area, right? So if you're passing a copy of a pointer, those two pointers point to the same thing. And then we have two types that are reference types that used to be pointers, but they were not. When we moved into Go 1.0, they were renamed, and the pointer disappeared. And what didn't disappear, it was hidden inside of the implementation. So a map is actually a pointer to a map, and a channel is a pointer to a channel. So when you do that, if you're passing a map and you modify it inside of a function, you're actually also modifying the original one. And same for channels. So this is a little bit, it feels like they're passed by reference, but they're actually not. It's just like a little design word. And this is one of the places where Go tries to be useful rather than elegant. And this is one of those places where it's like, well, otherwise you would have to pass pointers everywhere by using a map or a channel. And if you forgot that, then it will break, which would be even worse. So slices are not reference types, because if you have two different slices and you use append, for instance, if you are appending to this one, to the one inside of the function, it will not modify the original one, but it will modify the same backing array. So you need to be careful with that. It's still a copy. It's not a reference type, but it still points to the same area of memory behind. So you could have those side effects that we showed at the beginning. So you have all of these types, a bunch of different types. And these are all concrete types. Defining methods. We saw how to define methods. Oh yeah, more about defining methods. This is interesting. So we saw how to define methods on a person. But that is like defining a method in a class. In Go, you can define methods on anything, absolutely anything, as long as you give it a name. So for instance, you can define a type, which is an integer. There's no class, there's no struct. It's just an integer, name number, and you can say whether it's positive or not. Or even cooler, you can define a function, which is a mathematical function, which is a func that receives a float 64 and returns a float 64, and then define a map method on it that, given a slice, returns a slice where you've applied that function in every single one of them. So you can define methods on functions. And this feels weird, but in the standard library, we actually do it. There's a type of function, which is an HTTP handler, and it satisfies an interface by defining a method on that function. And it's kind of weird, but also I think it's one of the coolest things in Go, is the fact that anything can have methods. You can define them on top of that. And anything can have methods as long as you're defining those methods on things you declare to yourself. So you can now go and say, ooh, I have a string. I'm going to change the way it works by adding a method here and what. No, you cannot do that. That is what we call in Ruby. It's called what is the monkey patching? Yeah, there's no monkey patching in Go. There's no way to do that except for some weird ways that we can talk about if you're interested, and we use them only for testing. One more thing, Go does not support inheritance. There's no inheritance in Go. Why? There's good reasons for this, and the good reason is that we've used inheritance for a long time, and we've seen that it's very dangerous because you can actually write code that is wrong in very subtle ways. So let's see an example. This is Java, okay? So I have someone just like, oh. So this is Java, and what we're having here is this class runner, and the class runner has two methods, run and run all. It also has a name that has a getter. So when you run a task, and when you run all, what you're doing is you're running every single one of those tasks that you've been given. Pretty straightforward. Then you have a round counter class. And a round counter, it's a runner that counts. So of course, it is a runner. So therefore, we use inheritance. So we say a round counter extends runner. What we do is we override, so we add a counter, and we override both run and run all to call the parent run and run all methods, but at the same time, increase the counter. And then we add a get count for the counter. Cool. How many of you know about Java? Okay, so the next question is, so if I pass 3 tasks, 1, 2, 3, and I run them with round counter, and then I print get count, how many will I get? It would make sense that it's 3. It would be 6. Why? Because actually, when you're overriding something, what I thought I was doing was by overriding run all, and run is because in case you call run, I need to count +1, right? But actually, run all here in the runner, what it's doing, it's actually not calling run directly, but this run is going to call, run all is going to call run here, which means that now you're counting everything twice. And of course, the fix to that is only count it when you need to. But the thing is that the type system will not protect you from these kind of mistakes. And these are very subtle. In this case, it's very clear. But in some cases, it can be really complicated. So this is what we call weak encapsulation by inheritance, basically. And it's something that many languages have. And it's really hard to solve. So in Go, we solved it by removing it. So instead, we don't have inheritance. We have only composition. So in Java, you write this, composition. The problem with composition is that, of course, you need to redefine things. So this, just the beginning, continues here. So that get name, you're actually returning the get name of the one that you've composed, right? And this is not elegant. You're copy-pasting a lot of code. And if you're writing with Eclipse or something, you can probably auto-generate this, but you still need to read it. So in Go, what we did, so the pros, yeah, the bug is gone. But which is, it's nice, and everything just works correctly, and runner and run counter are independent, so that weak composition is gone. But we are redefining things. So get name, for instance, is something that you need to define many times. And if get name was one of them, there's only one, it's fine. But if you have, like, imagine you have 20, then now you need to redefine those 20. So in Go, so this is the runner type. So run and run all, they look basically the same. So the way we're going to do it is also by composition. So we're going to have run runner, and we're going to have the same issue of having to redefine the name method to call name. But we have also this thing called struct embedding. And struct embedding is something that I have not seen in any other language. Something similar to Ruby. I forgot the name, but Ruby has something similar to this. Mixins, I think they're called. And in Go, basically what you can do is define a field that is inside of your struct, but you do not give it a name. By doing that, what you're doing is you're exposing all of the things that are exposed in that type into your own type. Okay, so that looks like inheritance. So if I call getName on the big type, it will actually try to call it into the type that is embedded. But at the same time, it's composition, which means that there's no weak encapsulation. So basically, here what we can do is just write like this. You have the type route counter has a field called runner. The runner type. There's no runner name. There's no name, just a type. And with this, you can just change the thing, and now the name method is implicit. It's actually exported from the embedded type. So this is something that is used quite often, and it can make your code much more compact. So, but it's literally just syntax sugar. There's no other things. It's exactly like defining it with runner name and just copy-pasting every single one of those methods, but you don't need to do that. There's one more thing, which is the error type. And the error type is the only type that is pre-declared, that is not a concrete type. There's an interface, and its error returns a string. So anything that has that method will work. We'll talk about interface in a second. And the type of code you're going to see is this. If do something returns an error, and that error is not nil, then you're going to return it, or you're going to handle it somehow. You could return the error directly. In general, we do this. Thump.errorf, where you're going to generate a new error with some context. Instead of doing this, there's also an errors package that Dave Cheney created that works really well. And I would recommend doing that, but it's a little bit more advanced. Cool. So now we're going to talk about concrete types. And I'm not going to finish all the content, and that I knew that will happen. But there's much more content that is more advanced that you can look at later on. I'll share the slides with you. So what are abstract types in Go? So the ones that are not concrete. They do not talk about memory. They talk about behavior. So instead of talking about fields or memory layout, we talk about methods, only methods. So here, for instance, we have type positiver, and that is a weird thing that we do in Go. The name of the interface tends to be the name of the method plus R, except for error, because it would be really weird to pronounce. But other than that, in general, you're going to see this positive, 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 which is not English, but whatever. So we have two interfaces here, type reader, type writer. And these are defined in the I/O package. These are things that you're going to be seeing all the time as soon as you start doing any kind of streaming. When you have a file is a reader and a writer. When you have a HTTP network connection, is a reader and a writer. When you have a gzip decoder, is it a reader? When you have a gzip encoder, is it a writer? It is a writer. And this means that with this, you start creating some kind of set of concrete types. So an abstract type, in interface, it's just basically a membership test for a set of concrete types. That's how it works. There's no other things. There's no extends. And so you don't need to say this type extends, no implements. So you don't need to say this type implement this interface. If the type has all of the methods of the interface, you're good. So it's kind of like duck typing in Python, except that rather than being checked at runtime, that is checked at compile time. So instead of being something that you were going to get the exception later on, you will simply not compile saying you cannot use this type as that interface because you're missing these methods. You can also have type read writer, which is a read and a writer. This is also defined in the standard library. And when you define this, you can also define it like this. You can say a read writer is both a reader and a writer. So you can have basically interface union. And when you're doing an interface union, what you're doing is you're defining a union, an interface that has more constraints. Therefore, the number of types that are inside of that, that are implementing that interface will be smaller. So here, for instance, we have IO writer, it's all of those types. IO reader, it's all of those types. And IO read writer is the intersection of those sets. So, what is the one that is outside? What is the interface that covers all of the types? So it's the opposite, right? Like if we have, by doing the union of interfaces, you get the intersection of concrete types. By doing the intersection of the interfaces, you get the union of the concrete types. The intersection of reader and writer is nothing. So it's the empty interface. The empty interface is an interface that covers all of the types in Go. When you pass an empty interface, it's almost like in C when you have a void pointer, except that you're not losing any type information. You can actually go back to something else. So that's why one of the Go proverbs, which is a really good talk, by the way, if you want to learn a little bit more about the philosophy of Go, it says empty interface says nothing. And it is true. It's basically, I'm telling you, have this value, good luck. There's nothing that you can do with it other than actually checking, are you this type? Are you this type? Are you this type? And eventually it's like, ooh, you're this type, I know how to use it. But if you do not know what it is, there's nothing you can do. And I'm going to show this really quick, and I'm going to jump like 50 slides because there's a lot of really detailed thing on explaining how interfaces work. But interfaces in Go, they're used at writing generic algorithms like in any other language. In Go, there's no generics, there's no templates yet, and hopefully never. But I gave a talk about that on Monday. I'll share the video once it comes out. To hide implementation details too. So for instance, when you're returning an error, that error is an interface. You don't really care what's behind. You just care about the fact that there was an error. And if you actually care about what's behind, you can actually check. But the default behavior doesn't need to know that implementation. And also providing interception points. So now is the part where I pass all of this. So you can look at that later. Okay, so what's new? What is the difference between Python interfaces, which do not exist, so that's a difference, or C++ interfaces, which do not exist either, so that's also a difference. So the basic difference between interfaces in most languages, or abstract classes in Python, or interfaces in Java and Go, is the fact that the satisfaction of the interface is implicit. And this is actually something that is really important, because it means that there's no implements. So let me show you real quick my first Go program ever. There's a little HTTP, a little web page that you give some function, and it will draw it on an image. So I created 2 packages. One is the Parse Package, because I'm a software engineer. I design things thoroughly. So they have this Parse Package that has a parse function that, given a string, returns a pointer to a function. It would also return an error, because that could be wrong, but let's just go with the overall idea. So that function has a method eval. So I can call eval x and returns another float. So with this, I can now define my draw package that imports parse, and given a function that has been parsed, it just goes over all the possible values, prints the thing, and then generates the image. Cool. So basically, the package draw depends on the package parse. And this makes sense, right? Now, the problem is, if you want to test it, what you need to do is, in order to test draw, you need to first generate values of the parse func. You need to generate those. And that might be hard. In this case, it's easy. But imagine that you are, for instance, depending on files. Creating a file every single time you need to test something can be hard. So the solution with explicit satisfaction would be to have one extra package on top, right? You would have that interface that func parse satisfies, so implements, and then you would use it in the package draw. And now you can have other implementations of that common interface, and then you can test it easily. But now you added a third package, just because you don't want these 2 to depend on each other. In Go, you would do this. You just drop the common package, and the way you do this is by, instead of importing parse, and depending on parse.func, you define an interface that has the methods you care about. Right? So what you're doing here is actually breaking the dependency, and instead of saying I accept a parse.func, you're saying I accept anything as long as this method is there. And now you can use the parse.func directly with this package. They do not need to know each other. So the dependency has been completely broken, which means that testing this is going to be much easier. Now I can easily get like the sinus function and just pass it there. And it will just work, because it's the good type. Like I can say, I'm going to have this type of function that is a func float64 to float64, define the method eval on the function, I'm done. I can test it with anything. So interfaces can break dependencies. And this is something that makes the standard library possible. The standard library, without this, would actually have packages depending on each other. And this is something that Go does not allow. In Go, circular dependencies are not allowed. In C++, there are forward declarations and stuff that make it possible. In Go, that's not a thing. There's no forward declaration. So this means that this is actually a very essential thing. And this is something that if you start writing Go, it's going to take some time to get the thing. It takes some time to actually understand why this helps you design better systems. But it's something that you should keep in mind and try to use it as much as possible. The little detail is the interface will be declared where you use it, right? Using the evaluator interface when you're going to pass it to a function, not where you define in the struct. Otherwise, you would still have that dependency. So yeah, define interfaces where you use them. Oh, I was too fast. Actually, yeah, we have time to the last thing, which is type assertions. So type assertions are really cool because what I told you about, if I give you an empty interface, you cannot do anything with it. Actually, that is not true. If you know what could be inside, you can check whether something satisfies an interface or is of a given type, and then use it in that way. So, for instance, you can have a type assertion from an empty interface to a concrete type. So you can say, hey, is this an int? And if you do I : v dot int, like this looks like a weird function code without a name, that is a type assertion. And it will return int into I, or it will panic. It will panic saying, nope, that was not the type, sorry. If you don't want to panic, you can use secondary syntax, which is I, OK. And this is something that you see pretty often in Go. That I, OK means that that OK is going to be true if whatever you were doing succeeded. So in this case, v.int will return either 0 and false, or the value of the integer and true. Okay? So with this, you can start doing more interesting things. You can also do a switch on types. So you can say, I'm going to do a switch on that type, and if it's an integer, I'm going to do something. If it's something else, I'm going to do something different. So these are the kind of things you're going to see in the thumped package, for instance. What we're going to do is I'm going to try to print this. Is this an integer? No. Is this a float? No. Depending on what it is, you're going to be printing something different. You can even define a variable of the type of the type behind the interface. So in here, for instance, t will be of type int. But here, t will be of type empty interface. So you can actually make your code a little bit more compact by having one fewer type assertion. Now, this is something that I do not recommend doing unless it is the only solution, because this does not scale. Imagine that you now have, okay, int, sure. Ooh, also int 64, okay, cool. One more case. Also int 32, okay, and also int 8, okay, and then the float and the complexes. No, that will not scale, right? So normally what you're going to do instead, you're going to check whether the behavior, where you know how to handle the behavior of the type that you're given. Not exactly the type, but its behavior. So you can do type assertions to interfaces. And now what you're saying is the backing type, no, does the backing type satisfy this interface? So whatever is behind v, does it have a string method, which is a stringer, right? And if you do this now, what you can do is, well, if this is a stringer, then just call the string method on it, right? And when you're doing this is exactly what the thumb package does. So this is also a little bit of a way to extend your own type, your own systems, on saying, oh, if you satisfy the string method, I'm going to be calling that one. If you satisfy this error method, I'm going to be calling that one, right? So it's a little bit how the thumb package itself works. So here, for instance, yeah, s.string, we can call it because we know that it satisfies stringer. We do not know what type it is behind. We do not care. It's a stringer. We use it as a stringer. We just care about the behavior itself. So yeah, as I was saying, there's many types in the standard library that offer interfaces. And when a package in the standard library exports an interface, in general, that's an extension point. That's an opportunity for you to modify the behavior of the package. So use stringer. Stringer will print whatever you give it without asking you how, right? So if you pass a struct, it will just print it in a very defined way. Now, if you want to modify how that struct is printed, you can define a string method on it. You will make it define the string, satisfy the stringer interface, and then thumped will be able to call that method specifically. Same for JSON marshaller or a marshaller. If you want to change how things are encoded in JSON or XML, all of those interfaces are defined specifically for this purpose. So yeah, always say if you're starting to discover a new package, make sure that you go and you find all the exported interfaces, because those are really interesting. Those are the ones that are going to give you hints on how to use the package in an advanced way. And that's it for today, which I went a little bit late, but I don't know if you have a minute for questions or something. Okay, so yeah, we have a minute for questions. Otherwise, I'm going to add one thing here, which is my email. So if you have follow-up questions, feel free to send emails there, and I'll answer them tomorrow or on Friday. Questions, that was a lot of information, I know.
Slides available?
Slides available, yeah, I will share them with her, and then she can share them with all of you.
Hello, first of all, thank you very much for your talk, it was lovely. I have a lot of questions, but I have a very specific one. Could you please go back to your draw slide?
Yes. Actually.
Sorry for that. There.
Oh, this one?
No, where you use the evaluator.
This one.
There. If the evaluator was unexported here, it would still work, right?
Yes, it would still work.
Should we do it?
It is, so you can have unexported things, unexported types in an exported method or in function in this case. The exported draw function could return a not exported type or receive an unexported type. It is possible. It is pretty ugly. I would avoid doing that as much as possible. There's some random cases where it actually makes sense, but in general I would avoid it Because the problem is that then you would have a function that says, ooh, you need to give me a function of this, value of this interface. And by the way, this interface is, you cannot know. So it's kind of useless, but in some cases, that's actually what you want.
Are we gaining anything by making it unexported in any case?
Not really, no. Not in this case, no. There's also a very interesting trick, which is if you define an interface exported that has a non-exported method, you make that interface not implementable by anyone other than yourself. So there's some weird tricks that you can do, which I recommend avoiding as much as possible unless you actually need them.
Thank you very much.
Thank you. Okay.
Maybe the last question, if you have.
I have
Okay.
about the same slide.
Yeah, okay, cool. Thank you. I appreciate it.
So if this evaluator interface, can I also define this declare this interface in another place with the same name?
Yeah.
And what if I declare this interface with another name but with that same function inside?
So that's a very good question. So if you had two interfaces that have the same methods and the same types inside, but their names are different, or even their names are the same but they're in different packages, they're still different types, which means that this function, if you passed the wrong interface, it would complain. But it would only complain if you try to use the type of this function and say you had like common.evaluator, okay? So if you try to use this function and store it in a variable of type function that receives a common.evaluator and returns an image.image, that will not work. That is the only case where it will not work. If you're passing values, if you're using this, since both are the same ones and both basically define the same set of concrete types, that will work. But there's that weird case where it would not work, which means that if you had a function, if you had an interface that had a method that had an interface, and that interface you had two different kinds, the two interfaces would be different, which is a little bit more advanced and confusing. But in general, two interfaces are exactly the same if they have the same contents, except for the type itself. I don't know if that was clear or not.
Thank you.
Okay, thank you.
Okay, so thank you very much, everybody, and tomorrow we will continue.
Yeah, tomorrow we'll talk about concurrency and tooling about concurrency. Thank you.